This video is all about advanced collision theory. We're going to see how the ideal gas model connects to ideas from collision theory and unpack the Arrhenius equation a little bit more. First and foremost, though, I want to return to our model of an ideal gas. One of the key ideas from the ideal gas model in the kinetic molecular theory is that within a given sample of gas, particles are not moving at a uniform speed. There's a distribution of speeds. And if I pause this simulation briefly, we can see that distribution at the bottom of the simulation. There are many molecules that are moving relatively slowly in colors like blue and purple, and there are molecules that are moving relatively quickly in colors like yellow and white. And if we think back to the tenets of collision theory, the foundations of collision theory, one of the key ideas is that only molecules with sufficient energy are able to react. So only molecules that are moving relatively quickly, that have relatively high kinetic energy, for example, are going to react when they collide. And this is one of the key ideas of collision theory. Now, this probability distribution of the speeds has a mathematical form, right? It's a Maxwell distribution. We've seen that previously. And so we can find the fraction of molecules with energy above a certain cutoff by applying the mathematical form of this equation. And when we do that, we find that the fraction of molecules with an energy greater than some cutoff energy, for example, the activation energy for a reaction, is given by e to the negative e sub a divided by RT. And because this mathematical expression comes from the Maxwell-Boltzmann distribution, it's known as a Boltzmann factor. And this is exactly why this factor appears in the Arrhenius equation, because that entire equation and that entire model is based on treating the reactants as an ideal gas. And if we think through that kind of qualitatively, we can see how activation energy and temperature affect the number of molecules with sufficient energy to engage in reactions. So for example, in the figure you see here, on the left, we have two hypothetical activation energies represented by the vertical black arrows, a lower activation energy and a higher activation energy. And you can see that at the lower activation energy, we have this additional fraction of molecules that are able to react in the gold striped region. As the activation energy increases, we're kind of moving to the right along the kinetic energy axis, and the fraction of molecules with sufficient energy to react decreases as that activation energy goes up. This is what we would expect qualitatively, and the Boltzmann and Maxwell distributions just allow us to put a mathematical or graphical spin on this. On the right-hand side, we're seeing the impact of temperature. As the temperature goes up, we get more molecules with greater kinetic energy, moving at faster speeds. And you can see here that that increases the proportion of molecules with sufficient energy to react, even at a fixed activation energy, E sub A. So likewise, as we decrease the temperature, the fraction of reactive molecules decreases from the gold striped region to just the solid gold region, since we have fewer molecules with kinetic energy above E sub A at the lower temperature. To get an intuition for this, I encourage you to play around with an ideal gas simulation and look, for example, at what happens as we heat the sample and we get more molecules moving at faster speeds. This will give you good intuition and a good feel for why increasing temperature tends to increase the rate of reaction and increase the rate constant in accordance with this Boltzmann factor, e to the negative e sub a divided by RT. In the remainder of this video, we're going to put a mathematical and theoretical spin on collision theory, unpacking the frequency factor a little bit more and comparing the highly idealized predictions of collision theory with actual values, for example, for the frequency factor. To begin doing that, let's think about a very simple model of a chemical reaction as involving a collision between two molecules A and B that are not the same. They have different sizes. Let's just imagine that they're perfect spheres for the time being. We'll kind of unpack that here in a second. And so let's imagine that we've got two spheres with diameters d sub A and d sub B colliding in a reaction event. To think about what the idealized frequency factor is for this collision of two molecules A and B, well, it's going to depend on the velocities of A and B, their concentrations, and ultimately the frequency of collisions. And in order to think about that frequency, we need to think about the average relative velocity of A and B with respect to each other, which has a form like this. This actually comes from the kinetic molecular theory of gases, but uses a mass that is the reduced mass, an expression that includes the masses of both A and B and takes account of the fact that A and B may have unequal masses. It also uses the average or mean collision diameter, d sub AB, which is simply the numerical average of the A and B diameters. So the frequency of collisions here is that average relative velocity, UREL, pi d squared AB. Now it's worth noting that this pi d squared AB is an area, right? It's essentially the collision cross-section. It's the area over which reaction can occur, pi d squared. Concentration of A and concentration of B also appear there, since the greater those concentrations are, the greater the frequency of collisions. Now the reaction rate includes both that frequency of collisions, which we're calling Z, and the fraction of molecules with sufficient energy to react. And this is the fraction of molecules with energy greater than E sub A. And we've seen previously this is equal to the Boltzmann factor, e to the negative E sub A divided by RT. So here in this equation, we're taking Z, which we identified as UREL pi d squared AB, and as well as the concentration terms, A and B, and multiplying it by the Boltzmann factor underlined here in red. And so if we pack together all of the terms that do not involve the Boltzmann factor or the concentrations, we come up with the conclusion that the idealized frequency factor is that average relative velocity times the collision cross-section pi d squared AB. This gives us a highly idealized, highly theoretical measure of what the frequency factor should be, treating the molecules as spherical and basically imagining that every collision with sufficient energy leads to reaction. Now, of course, in practice, this isn't actually what happens, right? For most reactions, the measured frequency factor is much, much less than this idealized collision theory frequency factor because of the orientation issue. Molecules are not spherically shaped, and not all collisions lead to reaction just because of orientational issues, like we saw for the reaction of CO with O2 previously. To account for this, we can take the ratio of a measured frequency factor to the collision theory ideal and define what's called the steric factor. This gives us a measure essentially of the importance of orientational effects to the reaction. The smaller this number is, the more important orientational effects are in the reaction, right? With the hypothetical value of 1 being the greatest, in which case the measured frequency factor is exactly equal to the collision theory ideal. And so we can sort of reimagine the measured frequency factor then as the steric factor times the collision theory ideal, which is that average relative velocity times the collisional cross-section. This was a very quick overview of advanced collision theory. I would encourage you to check out these notes, though, for more details. And these notes start from the basics of collision theory and our basic model for thinking about how a chemical reaction takes place through a collision and goes all the way through these advanced concepts. And I'll include a link to these notes in the description for the video.